And when we're done with this, we do have a case study, and then the rest of the time is yours. Either go work on your exam or stay in here and work on it. We have, on Thursday, we have a lab exam, which is respiratory and urinary. It's back to the 56 questions, all right? Pretty much evenly distributed between the respiratory and urinary system. And then we'll probably have about an hour and a half, hour and 40-minute lecture on the digestive system. Hopefully the lecture notes will be here by then. And then you're free to go and keep working, okay, or stay working or whatever you want. All right, so the Henderson-Hasselbalch equation is a recognition of the logarithmic relationship between the amount of bicarbonate ions and carbonic acid. All right, so pH is equal to a constant called the pK. And this is a recognition of the affinity, the dissociation rate between carbon dioxide and carbonic acid. All right, it's specific to temperature. So the value that we use is the pK of carbon dioxide and carbonic acid at at body temperature, 37 degrees. So if you look at the pK at cooler or hotter conditions, it will be different. All right, obviously temperature adds or removes energy from the reaction. So for our intents and purposes, this pK is equal to 6.1. And then we take the log of the relationship between bicarbonate ions and carbonic acid. So once we take that relationship, okay, divide those two numbers, get their log, we add it to 6.1, and we get the pH of a solution. All right, so that's the Henderson-Hasselbalch equation. Normal pH, what did I say it was? 7.4. All right, so normal pK is 6.1. That means that to get 7.4, we're going to need a 1.3. All right, and if you do an antilog, and we'll get into that in just a moment, the antilog of 1.3 is 20. So the log of 20 to 1 is equal to 1.3. We add that to 6.1 and we get 7.4. This is how we get that 20 to 1 ratio, okay, which we're going to come back and look at in just a moment. Normal values for bicarb are 24 milli equivalents per liter. Carbonic acid is a little harder to measure. All right, so what we use to measure when we're looking at patients is not the carbonic acid levels, but their carbon dioxide pressure, the tension, the pt.2 of carbon dioxide. So carbon dioxide, pCO2, in arterial blood is 40 millimeters of mercury. So that's what we're going to use for our normal values when we're trying to decide whether or not someone's values are above or below normal, okay, rather than a range.
What's the name mean?
The A for arterial, if it was a V, then our values would be 44, 45, okay? So remember, this is pCO2. So to get it to be carbonic acid, we have to multiply this number by 0.03. Anybody have a calculator? I believe it's 1.2.
Yes.
Okay? So 24, what's 24 divided by 1.2? 20. 20. Hence, 20 to 1. we put in 24 milliequivalents over a bicarbonate of 1.2. That's our 20-to-1 ratio. That's our normal amount of bicarbonate ions in the blood and carbon dioxide as carbonic acid in the blood. And when we have that value, our pH is 7.4. Okay? Everybody with me so far? Not quite? So we're taking in our pH range of 7.35 to 7.45. We're going to narrow it down and say that's what our aim is to get to that. And we have that pH when our bicarbonate levels are at 24 and our PCO2 in arterial blood is 40. Our pH is 7.4. Okay? And 24 to 1.2, we bring it down to our lowest common denominator is 20 to 1. All right? So whenever these ratios are 20 to 1, our pH is going to be 7.4. Now what about if my bicarbs are 48 and my carbonic acid is 2.4? What's my pH going to be? It's still going to be 7.4. Are my values normal for bicarb and carbonic acid? No, but my pH is normal because my ratio, so I might have too many carbonic. What if I have extreme vomiting and I lose hydrogen ions, so I have too many bicarbonates? What did we say our respiratory response was going to be? Decrease our respiratory rate, retain carbon dioxide. By retaining carbon dioxide, what's going to happen to my carbonic acid? It's going to rise. And here it's risen so much that it's enough to buffer the high levels of bicarbonate ions I have. This is probably from eating that whole bottle of Tums rather than vomiting, all right? My respiratory rate is probably so low I'm hardly getting enough oxygen. I might even be unconscious. But I've buffered my pH. So my pH is normal, all right? So when we look at a ratio of 20 to 1, that can tell us, any changes from that can tell us pretty quickly what changes are going on in the body, all right? So 20 to 1, now sometimes I refer to the carbonic acid as CO2 levels, okay? But you can't put 40 in here. 24 to 40 is not 20 to 1. So that 20 to 1 or 20 to 1.5 is actually referring to carbonic acid, which is a measurement of CO2. Okay? All right. So now let's look at some of those changes. All right? Can you erase this equation? We'll come back to it when we look at the homework exercise, but I want to pay some attention to this 20 to 1 ratio. Okay? So 20 to 1 is normal. Let's say that instead of 20 to 1, my ratio is 30 to 1. I have 30 milliequivalents of bicarb in my blood. And my PCO2 is 40. Okay, that would give me a ratio of 30 to 1. Is this, am I in acidosis or alkalosis? I have too much bicarb, but a normal amount of carbonic acid. Do I have enough hydrogen ions if my acid amount, remember this is carbonic acid, the CO2 value is my carbonic acid level. So that's normal, but I've added half again as many bicarbs. So I would be in alkalosis, okay? What we're saying when our bicarb is 20 to 1 is that we have a buffered situation where our ratio of bicarb to hydrogen is able to give us a pH of 7.4. Okay, if they were equal, it would be a pH of 7. So we have slightly more bicarb than we have carbonic acid, all right, because our normal pH is 7.4. If this increases, And this stays the same. Remember, this is from our carbonic acid. It's going to be derived from that. So if this increases, but this doesn't, we're going to have too much bicarb, not enough hydrogen. We're going to be in an alkaline condition. All right? So with a situation like this, we are in alkalosis. Does that make sense? Okay, now let's change it to 15 to what? 15 milliequivalents of bicarb, but still our PCO2 is normal. Out of sync, but which way? Acidosis. Now we have too many carbon dioxide molecules. We're making too much carbonic acid, and the hydrogen ions that are released, we don't have enough of our bicarb to buffer it. Okay? So we are in acidosis. So if this top number, which is our bicarb, goes above 20, we're in alkalosis. If it goes below 20, we're in acidosis. Okay? What was the cause? Was the cause a respiratory problem or a metabolic problem? By metabolic, I'm talking about the Tums, the diarrhea, the vomiting, the ketoacidosis. What's going to change our bicarbonate ion? The bottom number is carbonic acid. So that's our CO2. So this is a metabolic cause. When the top number changes, it's a metabolic problem. So this would be metabolic acidosis. And this would be, alkalosis, and this would be metabolic acidosis. So what would be some causes of metabolic alkalosis? Vomiting. Remember, we lose hydrogen, but we keep the bicarb. So excessive vomiting. An overdose of an antacid, Tums, Mylanta, whatever, anything that's going to make too much bicarbonates. Metabolic acidosis can be caused by diarrhea, ketoacidosis, someone who's a diabetic and is breaking down fatty acids and producing too many of those fatty acids for pH balance by the body. All right? So no, at this time, our carbon dioxide levels have stayed the same. Okay? Now let's change those levels, and we'll make this normal, 20, and we'll make this 0.5. So what have we done? We've breathed off. We don't have enough carbonic acid. So we're breathing off carbon dioxide. Remember, the one refers to carbonic acid coming from carbon dioxide. So if we don't have our normal amount of carbonic acid, it's because we don't have our normal amount of CO2. How do we lose CO2? Hyperventilation is about the only way. So we would be in, when the lower number changes, it's a respiratory problem. So we would be in respiratory alkalosis caused by hyperventilation. Now the hyperventilation may be due to panic. It may be due to high altitude. It may be due to improper breathing during labor. But whatever reason, we're blowing off CO2, hence our lower number. So this, a 0.5 would be a PCO2 of 20 millimeters. Okay, half of our normal amount of CO2 would give us a 0.5 in our ratio. All right. So we have more, even though our bicarbonate level is normal, we have too much bicarb for the amount of hydrogen ions we're able to release from our carbonic acid. That's why we're in alkalosis. But it's the CO2 levels that changed, so the cause is respiratory. All right? So what would have to happen to create respiratory acidosis?
You're like holding your breath or something?
What I'm saying, but what would happen to CO2 levels? Are they going to go up or are they going to go down if we're in acidosis? Up. All right? So if our ratio is 20 to 2, we have twice as much CO2 as we should have. All right, so we're in acidosis. The cause is not getting rid of our CO2. We're not breathing properly. And remember, it's a respiratory problem. So anything that's going to prevent us from breathing out the CO2, so any respiratory emphysema, pneumonia, any of our COPDs, pulmonary edema, okay, anything that's going to keep the CO2 in the blood and not allow it to get out of the blood and into the alveoli. Or if it's in the alveoli, to get out of the alveoli. So we have an increase in CO2, all right? Too much carbonic acid and not enough bicarbs to buffer it. So our pH is going to be too low, all right? So we can work it out. If our ratio is 20 to 2, all right, then we would be dividing by, we would be taking the log of 10 instead of 20. Anybody have a computer? What's the log of 10? I'm going to show you a logarithmic calculator on the internet so you guys don't have to buy.
I should know.
Log of 10 should be 1. 1, okay? So if I add 1 to 6.1, what's my pH? 7.1. Is that an acidic pH or a basic pH? That's an acidic pH, and I just got through saying we would have respiratory acidosis. Okay? Now, if all I did was I told you that an individual's pH was 7.1, would you be able to tell me if they were in acidosis or alkalosis? Yes. Would you be able to know the cause? Would you be able to tell me if it was a respiratory problem or a metabolic problem? No. If I give you this, can you tell me if they're in acidosis or alkalosis?
Yes.
Yes. Can you tell me the cause?
Yes.
Yes. At least whether it was respiratory or metabolic. You wouldn't know if it was pneumonia or COPD. Okay? And eventually you can figure out the pH as well. You do not need to have a calculator for your comprehensive exam. This is what you need to interpret based on this. Okay, I'm not going to give you equations where you have to figure out the pH or how much bicarb or CO2 might be present. Okay? All right, here's another situation. A ratio of 40 to 1.5. Acidosis or alkalosis? Alkalosis. My bicarbonate ions have doubled. They've gone from 24 almost, well, let's change, let's make it really, really, really doubled. They've gone from 24 to 48. So they've gone from a ratio of 20 to 40. My carbonic acid has only increased by 50%. Okay? So my PCO2, instead of being 40, is
40. 60.
half of that is 60. Okay? Which one changed the most? My bicarbonate doubled. It increased by 100%. My carbonic acid increased by 50%. Okay? So I have too many bicarbonate ions that I can buffer. So my condition is alkalosis. Is it respiratory or metabolic? It's metabolic. You take the number that has changed the most. All right? So I had vomiting, or I ate 6 bottles of Tums. I was on a bike ride and I cramped all over, so I just kept eating Tums and Tums and Tums and Tums. All right, so I'm in alkalosis and I'm in metabolic alkalosis. Why is my CO2, why is my carbonic acid up? What was my body trying to do? You know this already because we talked about it. What happens when your pH goes up? What happens to your respiratory rate? Your pH is going up. I have too many bicarbonate ions. My respiratory rate, I want to get more hydrogen ions, right? Because I have too many bicarbs. So I'm trying to increase my hydrogen ions so I can balance that. So that's right. My respiratory rate slows down as I try to hold on to CO2. Is that working? Am I holding on to CO2? I'm holding on to some. I've increased the amount of my PCO2 is higher. I've increased the amount of my carbonic acid. Is my pH normal? Is my pH 7.4?
No.
No. My pH would my carbonic acid levels would have to be 2 for it to have fully worked. All right? But I have started to compensate. So this is what we mean by partial compensation. Both numbers have changed. So my original problem was too much bicarb. I know that because this number has changed the most. I've started to alter my breathing in order to buffer those additional bicarbs by adding hydrogen ions from carbonic acid. So my CO2 levels are rising. But it's only partial compensation. Because my pH isn't normal. My ratio is not yet 20:1. Over here. Have I compensated at all? No. So on that homework, on the extra credit, or on any of the questions, if one of the values is still normal, here my CO2 value is normal. So I have metabolic alkalosis, uncompensated. If I was compensating, my CO2 levels would go up. Okay? Here I have respiratory acidosis. Okay? Too many hydrogen ions. To compensate, my bicarbs would go, well, here to compensate my, for this one, my bicarbs would, this is metabolic alkalosis, sorry, respiratory alkalosis. Too many bicarbs for a respiratory problem. To compensate, I would lose, this number would go down as I start to compensate, okay, to get rid of those bicarbs. So if one number is normal, be it the 20 or the 1, it's showing no compensation. If both numbers are abnormal but don't yet make a 20:1 ratio, then it's partial compensation, okay? If both numbers are abnormal but I have a 20:1 ratio, like 40:2, then it's fully compensated. If I had this ratio of 40:2, what would the pH be?
40:2, 7.4.
The same as 20:1, so that's going to equal a pH of 7.4. What caused this? Was this originally acidosis or alkalosis? You don't know. You don't know if the cause was respiratory or metabolic, which is why in the extra credit, I tell you. Okay, because if it's fully compensated, you have no idea. Yes?
So when both of the values like either double or shrink, it's fully compensated, right?
If the ratio comes out to 20:1 and your pH is 7.4, it's fully compensated. Okay? So for the extra credit, to be fully compensated, the pH has to be 7.4. Even though 7.37 is in our normal range, we'll consider it partial because it's not yet to 7.4. Okay? Yes, Andrew?
20:1 ratio, but it's not 20-1, 40-40.
It's 40-2, which is really, if we break it down to its lowest common denominator, is 20-1.
Okay.
So our pH is still going to be a 7.4. Okay?
Can I make, oh,
I don't. Go ahead.
okay. So for partial compensation, the ratio can still be 20-1. No? What is it?
No. It's, the numbers have both changed, and the ratio is not 20-1.
Okay.
So our pH is not 7.4.
Okay.
Okay? For no compensation, one number is still normal.
So as long as we're between 7.35 and 7.45, but not 7.4, we're still talking about partial
Yes.
compensation.
For the purposes of our exercise.
7.4, it will be
Yeah,
full
fully
compensation.
compensated. Okay, did anybody else have a question? All right, so let's take a look at, that's the concept that you need to understand for the comprehensive when it's not open book and take home and everything, okay? You don't need a calculator. If I give you a situation like this, you should be able to interpret whether it's acidosis or alkalosis, whether it's respiratory or metabolic, okay? Just those same questions, but I'm not going to ask you, I'm not going to give you this number and ask for the pH. Okay, so you don't need a calculator for that. Yes?
Some questions have like 15 to 0.9 rather than 1.
Okay.
Is that a huge difference?
So 15 to 0.9, is that a 20-to-1 ratio? No. Is one number normal? No. All right, so both numbers are off. Obviously, it's partial compensation because the 0.9 is not normal. We're starting to change. Which one's changed the most? The 15, decreased by 25%. So that's the cost, it's the metabolic cost. Okay? So you're starting to see compensation. We've lost bicarbonate ions, so now we're starting to lose the CO2 to compensate. Okay? All right, so let's look. You may not be aware. The directions, if you're interested in doing the extra credit acid base, sorry, put grades up there. Let me go to, I'm going to do it quickly. All right, so this is acid-base balance. It's in the urinary system. So under urinary labs, if you scroll down, it says extra credit acid-base balance right here. And then right below that, acid-base problems guide, solution guide. Acting like I already have it. Okay, so here's the easiest part. This is the first, there's 3 sections in your extra credit worksheet. First is just solving for pH, all right? So you're going to have the bicarbonate levels, and you're going to be given the PCO2. But remember, the PCO2 has to be converted to carbonic acid, because that's our 20-to-1 ratio. So Jackie has a PCO2 of 40. Is that normal or not?
No.
Yes.
Yes.
Yeah.
And our bicarbs are 38. Is that normal or not? No. So is this partially compensated or uncompensated? Uncompensated, because she has one normal value. All right, her PCO2 is unchanged, so she hasn't yet started to compensate. So we put 38 at the top, and we have to multiply 40 by 0.03 to get to our carbonic acid values. So that gives us 1.2, and which we already knew for our normal. Divide 38 by 1.2 and take the log of that number. So we're not taking the log of 38, okay? We're taking the log of this value divided by this value. So we do this first, and then we take the log of that value, and we get 1.5. So her pH is 7.6. Is she in alkalosis or acidosis? Alkalosis. Would we expect that from looking at this value?
Yes.
Yes, because her bicarbs are too high. All right, therefore, too many bicarbs for the amount of hydrogen ions. If she were to compensate, she would decrease her breathing and start to increase her CO2 values. Okay, but she hasn't done that yet. Her CO2 values are normal, so she is uncompensated. All right, so that's how you would solve for the pH in that first box. You're thinking this is a slide, it's not. So in the next box now, we're solving for bicarbs. All right, so this is anti-log. This gets a little confusing, which is why I ended up putting this up here, because I forget from year to year how to use my anti-log. On the computer, you can find an anti-log calculator or a logarithmic calculator. Okay, this is www.1728.org/logarithm. I'll write it up for you. But most simple calculators, even you don't have to have a fancy graphing one.
1728.org/logarithm. .htm.
.org/logarithm.
.htm.
All right, so what you do is right here in the middle, you decide if you want logarithm. So if I had 38, what was it? It's 32 point something. Not 32. And I wanted to find the logarithm of 32.5. I'd put it in there. Click enter, and down here at the bottom is my logarithm 1.5. Okay? So I'd add that to 6.1 and get a pH of 7.6. All right? Now, we want to figure out what her bicarbs are. So we're going to switch. We're going to take the let me go back to the previous slide, the previous page. We're going to move the pK over, okay? And we're going to subtract the pK from the pH. So move this over here and take the antilog of that. All right? So not the antilog of the whole. So we're solving for bicarb. So now we know that her PCO2 is 40 and her pH is 7.6. So we're going to take the antilog of 7.6 minus 6.1 and divide by her carbonic acid concentration. So we already knew that was 1.2. 7.6 minus 6.1 is 1.5. We multiply those two together. And now we take the antilog of that. All right, and we get 38. So usually if you have a calculator that has log on it, you have a second function, you hit second function and then log, and it should do antilog. If that doesn't make any sense, we can go into the computer calculator here and switch over here. This button says antilog. So it's taking the antilog of that number, and it's, I have to put the number in there. Take the antilog of 38. That wasn't the antilog, what was it? 1.5. And it gives me 38. 31. I think it was 1.6. 1.5? No, it was 1.6. Or whatever. Okay, 31.6. So you can just flip back and forth here if you can't figure out how to use the log and anti-log of your calculator. You can go on here and just switch. So anti-log of or log of. All right? And then you would do the same thing, except you would have the PCO2 in there. So now we want to know, well, how much PCO2 does she have? All right? And so I have this on there. You would just divide your bicarbs by the anti-log and multiply it by that conversion factor of 0.03. That's going to give you the carbonic acid component. Okay?
Professor?
Yes.
So we're going to be using the thing online and not the PCOX?
Right, for the extra credit one. So it's just that page that I have in there doesn't use it as the PCOX. I mean, you're welcome to do that just to practice. But this little table, these 2 sheets in here doesn't use PCOX. Okay? So, or you can just use a calculator. Either way will work. All right, but the underlying concept that I want you to be able to determine, this is just practicing with numbers and plugging them into once you've done one. The other 3 or 4 is just to practice. This is what I want you to understand and how this changes affect alkalosis or acidosis. Okay? All right, let's take a short break, just a 10-minute break, and then we have one case study, all right, and then we're done. You guys can either stay and work on your exam, stay and study for the lab exam, but after our case study, we'll study. You guys